The third one of the four fundamental subspaces is called the null space, and you have already learned about it in the last week or the week before, so this is more of a recap. And let's also write the fourth one, which is the same, except this is called the left null space. So they are pretty similar, you'll see in a moment. Okay, so we have the last two fundamental subspaces here. Let's define our matrix A, which is an n into m matrix. So the null space of this matrix is the set of all such vectors x so that x is equal to 0. So this is n into m, this has to be m into 1, and we get n into 1 0 vector, right? So all such vectors x that satisfies this equation makes up the vector space that is the null space. And you have already learned how do we determine the basis for the null space of a matrix in week 6 when we discussed in details about homogeneous systems. So I'm not going to go there in this video. All right, so let's move on to the fourth one, which is the left null space. And this is you can define it by the set of all such vectors y so that this equation is satisfied. So a is n into m. This vector has to be, this is a vector, so this is a row vector, which means x is a tall vector, so a component, so more like y transpose, because this vector is like this. If you knock it over on a side, you get something like this. So this is not m into 1 or n into 1, this is 1 into n, right? So this vector looks something like this on its side, equal to, which gives me 1 into m. This is another row vector, so very fat, very short vector. Anyway, so all such vectors y that satisfies this equation is called the left null space of the matrix A. So these two spaces are pretty similar, and the relationship between them is similar to the relationship between the column space and the row space of a matrix, because we know that the column space of a matrix is equal to the row space of the transpose of said matrix, which is the same in the case of these two as well, because if we take the transpose on both sides, we get the right hand side of this, and no, so you get xt A transpose equal ot. So the null space of a matrix is the left null space of the transpose of said matrix, because this is similar to this equation. So this is the null space of the matrix A. So null space of the matrix A is the same space as the left null space of the matrix A transpose. All right, so let's talk about the dimensions here. The dimension of the column space was the matrix is n into m, so the dimension of the column space was n, so this belongs to Rn, right? Rn. And the dimension of the row space was m, so this belongs to Rm. This belongs to Rn, this belongs to Rm. The left null space, let me write it a little bit differently. So the null space of the matrix A is the same. We are talking about the row space of column. We are talking about the row space of the matrix A now. Right? Forget about the equation. So the null space of matrix A, and we have got the left null space of the same matrix A. Okay, so the row space of the matrix A is belongs to Rm. The null space of the matrix A, if you recall from the last lecture, also belongs to Rm. So these two subspaces are subspaces of Rm. These two fundamental subspaces are going to be the subspaces of Rn. And there is a very interesting relationship here. What is the dimension of the column space? And what is the dimension of the row space? From last lecture, we know that they both have the same dimension, which is equal to R, given that this matrix A has rank R. What does rank R mean? Rank R mean there are R pivot elements. And what does R pivot elements mean? R pivot elements denote that the matrix have R linearly independent columns as well as R linearly independent rows. R linearly independent columns mean the column space has R dimension. That is why the dimension is equal to R for column space and for row space as well, because R rank means R pivots, and R pivots means there are R linearly independent rows, which means the dimension of the row space is also R. So the dimension of column space is equal to the dimension of row space. Now, from last week, you also know the dimension of the null space of matrix A is M minus R, and the dimension of left null space, because left null space is the null space of A transpose and column space is the row space of A transpose. So from this relation, we can say that the dimension of left null space is n minus r. Just transpose the matrix and the same thing applies to here as well. Alright, so we got a couple of new informations. We have the dimensions. Dimension of column space is equal to r. Dimension of row space is r as well. Dimension of null space of A is m minus r. Dimension of left null space of A is n minus r. These two are subspaces of Rn. These two are subspaces of Rm. Okay, there's one more interesting thing left to show, and that is the concept of orthogonal complement. So let's talk about orthogonal complements. Orthogonal complements. Two vector spaces are called orthogonal. Let's say U and V, two vector spaces. They're called orthogonal if any vector from U, let's say U, small u, and any vector from V, let's say small v, if they are perpendicular with each other, which means if you take the dot product or inner product, you will get 0, which means these two vector spaces are orthogonal. Let me recap. Any vector from this space, any vector from this space, if they are orthogonal for all vectors of these vector spaces, we say that the vector space U and the vector space V are orthogonal. A good example would be, let's say, in the 2D space, this is R2, this is a subspace, right? This line right here. This line, not quite right, this line is another subspace. Both of these subspaces have dimension 1, this is dimension 1, this dimension 1. Any vector on this line, let's take any vector from this line. So let me choose this vector, and let me choose any vector from this line as well. They are going to be perpendicular, and this applies for any vector of these two one-dimensional lines. So we say that this vector space, let's call it U, and this line, let's call it V. These two vector spaces are orthogonal. Now, to be orthogonal complements, it is not enough for two vector spaces to be orthogonal. They also have to be complete. And by that, I mean Let me just get rid of this here. All right, so let's say two vectors u and v. U and v are orthogonal and they are both subspaces of Rn, let's say. If they are orthogonal and if dimension of u plus dimension of v equals to n, then we say not just u and v are orthogonal, they are orthogonal complements of each other. And if we define them in words, the orthogonal complement of a vector space U is the set of all such vectors that are orthogonal to the vectors, to all vectors of U. So all such vectors, this is the keyword, all such vectors. It is just not enough that the vectors of V are orthogonal to U. All the vectors that are orthogonal to U must be inside V as well. So all such vectors, this is the keyword. Anyway, I think that should clear you up enough. If not, this equation will tell the rest of the story. Anyway, so that is the orthogonal complement, and from our relationship here we can say that we can see that the dimension of this plus dimension of this is equal to m, and they are both sorry, not this one, the dimension of this and the dimension of this, if we add them together we get m, and they are both subspaces of Rm. The dimension of this and the dimension of this equal to n, and they're both subspaces of Rn. So it looks like we have something here. So let's see if the row space and the null space of a matrix are orthogonal and orthogonal complements, and as it turns out they are. So let's prove that. We have Ax is equal to 0. This is the definition of all such vectors of x will create the null space. So this defines the null space of the matrix A. Now let's write it like this. So we have row 1, row 2, row 3, dot dot dot. We have x1, x2, dot dot dot. We have up to Rn, xn is equal to 0, 0. There are n zeros. So row 1 into x1 is equal to 0. So sorry, not x1. I should not have broken it down. Let's just call it the vector x. So from matrix multiplication we can say that row 1 into the vector x is equal to 0. So the first row into this vector gives me the first element of here. Row 2 into x is equal to 0. And row 3 into x is equal to 0, so on and so forth, which means all the rows are orthogonal to the vector x, any such vector x for which this equation holds. And the row space is defined by the linear combination of these rows. So any vector of the row space is orthogonal to any such vector x. So we have our proof. The row space, any vector in the row space is going to be orthogonal to any vector of the null space of A. Alright, so they are orthogonal and their dimension equals to, as we saw, the row space and the null space, their dimension equals to m. So their dimension, not just they are orthogonal, their dimension of our row space plus the dimension of the null space, they equal to m. They are both subspaces of Rm. So as you can see, we have proved that these two vector spaces, the row space and the null space of a matrix, are orthogonal complements. And if we complement transpose this, so let's take the row space of A transpose and the null space of A transpose. As this applies for any matrix, the row space of A transpose is also the orthogonal complement of the null space of A transpose, because this property applies to any matrix. But the row space of A transpose is just the common space of A, and the null space of A transpose is just the left null space of A. So similarly, we can say that the common space of a matrix is the orthogonal complement of the left null space of the same matrix. All right, so this is the last piece of information. These are the four fundamental subspaces of a matrix. This is their dimension. Column space and left null space are subspaces of Rn. Row space and null space are subspaces of Rm, and also now we know that these two vector spaces are orthogonal complements of each other, and these two vector spaces are orthogonal complements of each other as well. All right, so I think that's all you need to know about the four fundamental subspaces for now, and that concludes our lecture.